Hello. In today's video, we're going to start Chapter 8, titled Hypothesis Testing. In this video, we will cover Section 8.1, the basics of hypothesis testing. The key concept in this chapter is to present the formal components of hypothesis testing. We will go through all steps, finding various variables in these instances. And by the end of this chapter, we will apply the theory of hypothesis testing to proportions and means. First, we have to define what a hypothesis and what a hypothesis test is. And we should already have an intuition for a hypothesis, right? A hypothesis is a claim about some property of a population. The two types of claims we will talk about are hypothesi about a population proportion and a hypothesis about a population mean. The hypothesis test, or a test of significance, will be the formal procedure for testing this claim. If we make some sort of initial hypothesis, we want a method to be able to determine whether that hypothesis is able to be rejected or not rejected. And that is what we will lay out today. So let's look at an example which will follow us through today's video. Suppose 1,009 consumers were asked if they were comfortable with having drones deliver their purchases, right? This is an actual proposition by Amazon that they might be able to do some sort of prime delivery within a day if they were allowed to have drones. Let's suppose that 54% of them, which turns out to be 545 of them, responded no, they are not comfortable. What we need to do is develop this robust system of notation. P is going to denote the proportion of consumers not comfortable with drone deliveries. The majority claim, right? We're trying to claim a majority of consumers are not comfortable with drone deliveries is equivalent to the claim that the proportion is greater than a half, so that P is greater than 0.5. This is our expression of our original claim, that the proportion of adults is greater than a half. And so what we're trying to understand is the big picture, that our claim is that the majority, the proportion P, the majority of adults uncomfortable is greater than 0.5. So among those 1,009 consumers, how many do we need to be uncomfortable to have a significantly high number? Is just 506, which is 51%, is that significantly high? Clearly no. If I get 1,006, that would be about 99.7% of the respondents. That is clearly significantly high. But what about the sample we got of 54% or 545 adults asking the survey? Is that significantly high? That is our main question. Did we get a value that is significantly high, or do we have a value that falls within a regular accepted range? That is what hypothesis testing will allow us to determine. The way that we're going to measure whether something is significant or not is by that same value of significance we've dealt with before, that alpha. And so hypothesis tests, as we've stated, are also called tests of significance. And we use probabilities in an earlier section to determine whether things were significantly high or significantly low. In this chapter, we're going to formalize those concepts in kind of a universal procedure that is used throughout many different fields of application, which is more than just determining whether we are 2 standard deviations above or below the mean. And the way we do this is by developing a robust set of hypotheses. The first hypothesis we set is called the null hypothesis, which we denote as H sub 0. In the null hypothesis, we look at the statement of the value of the population that is equal to some claimed value. The second hypothesis, or the alternative hypothesis, which we denote by h sub 1, there are other values, h sub lowercase a or h sub uppercase a, but we will denote it as h sub 1, is the statement that the parameter has a value that is somehow different than the null hypothesis. The most common alternative hypothesis uses the symbols less than, greater than, or not equal to. We will build null and alternative hypothesis later. Here is the procedure for hypothesis testing. And I know it looks a little confusing, so let's go through it kind of piece by piece. The first thing we must do is identify the claim. I need to know what my original claim is. Then we need to determine the symbolic form. We've already done this in that first example, but we'll go through all of these steps in a more formal way later on. The third step is we need to build the alternative hypothesis and then the null hypothesis. The alternative hypothesis is the one that does not contain the equality, whereas the null hypothesis is the hypothesis that does contain equality. The fourth step is determining our significance level. This will be very similar, but somehow slightly different than what we did before with determining alpha and our confidence levels in Chapter 7. Next, we need to identify the test statistic, such as the normal test statistic or the t-test statistic. There is one called the chi-squared, which we will not cover. This test statistic will be the value that helps determine whether our claim is significantly high or not. There are two methods to help us determine this. One is called the p-value method, p standing for probability. And what we do in the p-value method is take the test statistic and turn it into a probability value. And if the probability value is less than our significance level, alpha, what we say is we reject the null hypothesis H0. If the p-value is larger than our significance level, then we fail to reject the hypothesis test, the null hypothesis. The other method, called the critical value method, uses the test statistic and determines an area underneath either the normal or the t-distribution. If our test statistic is within what we call the critical region, we get to reject the null hypothesis. And if the test statistic falls outside of this critical region, we fail to reject the null hypothesis. And this critical region we'll define later, but this critical region is dependent on our significance level alpha. Lastly, we want to restate the decision in these non-technical, non-symbolic terms. We'll state whether we reject the null hypothesis or we fail to reject the null hypothesis. We'll see moving forward exactly what that means. But this, overall, is a snapshot of the process. So let's get down to the nitty-gritty. The first three steps require further explanation. How do we turn the original claim into a null hypothesis and alternative hypothesis? First, we need to identify the claim to be tested and express it in a symbolic form. Next, we must give the symbolic form that must be true when our original claim is false. Then, we need to consider two symbolic expressions obtained. The alternative hypothesis is the one that does not contain equality. The null hypothesis is the one that contains equality, where our parameter is equal to the fixed value being considered. Okay, let's go through this first example. So we want to use the drone delivery example to set up our hypothesis test. So the claim we had was the majority of consumers are uncomfortable with drone delivery. So our original claim is that the majority are uncomfortable. The symbolic way we would write that would be that P is greater than 0.5. That would be the majority. Step 2 says we want to give a symbolic form that must be true when the original claim is false. What that means is if this is our original claim in symbolic form, what would make that false? Well, all we have to do is switch our sign, switch our comparison sign. So this is what it would be to be false, that the population proportion would be less than 0.5. Now we can start to determine the null and alternative hypothesis. If we identify H1, our alternative hypothesis, it will be of these two, which one that does not contain the equality. Because this is less than or equal to 0.5, it contains the equality, I do not want to include that as my alternative hypothesis. My alternative hypothesis would be our original claim. The null hypothesis will always be our parameter being equal to our value. Here are our alternative hypothesis and our null hypothesis together. It turns out that most of the time, and kind of a quick little hint, that most of the time, the original claim and the alternative hypothesis will be the same. That won't be true 100% of the time, but more often than not, that will be true. That is the first 3 steps of hypothesis testing done. What we need to do now is come up with our test statistic and determine whether we can reject or whether we fail to reject the null hypothesis right here using either the p-value or critical value method. So let's talk about the test statistic. When dealing with our test statistic, the most important thing is what we compare our test statistic to, and that is our significance level. Our significance level alpha for the hypothesis test is the probability value we use as the cutoff for determining the value of our significance. Alpha is the probability of making a mistake, of rejecting a null hypothesis when it is true. The significance level alpha that we get will be very similar to the ones that we use as our critical values in Chapter 7, Section 1. The most common choices for alphas are 0.5, 0.05, 0.01, and 0.1. 0.05 is the most common choice for alpha. Once we know our significance level, which will be determined in the problem for us, we'll need to find our test statistic. Our test statistic will either come from the normal distribution or the t-distribution. We will not cover the chi-squared distribution, which deals with variances and standard deviations. The table that we were about to show gives us exactly the type of test statistic we're going to use and the formula that we're going to use. Like we said, when we do this hypothesis testing, we will cover proportion and means of a population. If we're trying to test a claim about a proportion, we will always use the normal distribution. And the test statistic we will use is this formula. Z is equal to p hat minus p divided by the square root of pq over n. If we're testing a claim about the mean, Again, just like in chapter 7, when we're doing any sort of confidence intervals with the mean, we can either not know our standard deviation or we could know our standard deviation. If our standard deviation is not known, we needed to rely on the student t-distribution. And we get this formula for the t-distribution being x bar minus mu divided by s over the square root of n. If we do know our sigma, we get to change to a normal distribution. And notice these formulas here are almost identical. The only difference is we have the sample standard deviation in the t-distribution and the population standard deviation in the z normal distribution. And they are separate distributions. We will not cover the chi-squared. And don't worry, we will go through examples of these so we see exactly what's going on. We will not have to use all of them in one problem. We will only ever be using one of these in one problem. So, in our example of drone deliveries, our claim is that the population proportion is greater than 0.5. And recall, our alternative hypothesis was that claim. Our null hypothesis was that the proportion was equal to 0.5. What we want to do is find the value of our test statistic and then use the p-value or the critical value. These are two different methods for determining whether we can reject the null hypothesis or whether we can fail to reject the null hypothesis. Again, our test statistic is the value that we're going to use to make these decisions. They are found by converting our sample statistic, like the sample proportion or the sample mean, into a z-score or t-score, with the assumption that our null hypothesis is true. So, we have our claim. Our null hypothesis is that p is equal to 0.5. So, we are working with the assumption that our population proportion is 0.5, and our Q value, again, is 1 minus P. So our Q value is 0.5 as well. Our sample proportion is going to be 0.54. Remember, the survey said that 54% of respondents. That tells us our sample proportion is 0.54. And so what we can do now is compute our test statistic relating to this information. So to compute our test statistic, we use the formula where z is equal to p hat minus p all over the square root of pq over n. Right? Our test statistic from the table before that deals with proportion. Our sample proportion was 0.54. Our population proportion was 0.5. And I'll put in the other values. So 0.5 times 0.5 all over 1009. That was the number of people in our survey. If I compute this, I'll get 2.54. And again, this test statistic is going to be a z-score that we're going to have to compute the area behind or to the right of eventually. So we want to round up to 2 decimal places. So our z-score, or our test statistic in this case, is 2.54. Once we've found our test statistic and have our significance level, what we need to do is determine our critical region. The critical region, or rejection region, is going to be the area that corresponds to all the values of our test statistic that will cause us to reject the null hypothesis. Here are the 3 different types of critical regions we can have, and they are called different-tailed tests. We have what's called a two-tailed test. This occurs when our alternative hypothesis has a not equals in it. If our alternative hypothesis is that our parameter is not equals, that means we could be off to the left or to the right, which means I have two values that I could be off by, which means I need two quote unquote tails. The left-tailed test is when my alternative hypothesis has a less than sign in it. If I'm looking at all the values that are less than, that means I want everything to the left, which means my critical region or my rejection region is going to be values to the left. A right-tailed test deals with having an alternative hypothesis with a greater than sign. If I'm greater than, that means I want areas to the right. And my tail or rejection region is going to be areas to the right of some given z-score. So let's look at the first of these two methods, the p-value method. In the p-value method, we're looking for a probability of getting a value of the test statistic that is at least as extreme as the test statistic we obtained, right? This test statistic came from our sample data. There's a chance this value we got from the sample data is significantly high. And if the probability of getting that value is very low, that means that we have a significantly high valued number. And the way we do this is by turning our test statistic into a probability. Here's how we do this. Our alternative hypothesis was that the proportion was greater than 0.5. Because I had the greater sign, that tells me I have a right-tailed test. So when I look at my distribution, what I plot here is my z-score, my test statistic of z being 0.54. If I have a right-tailed test, that tells me that all of the rejection regions has to be to the right of this thing. So what I'm looking for a p-value, my probability value, is I'm looking for the probability that any other value is greater than 2.54. Well, this is a normal distribution. I know exactly how to find an area to the right. Recall, our table tells us areas to the left, so I can just compute 1 minus the area to the left. So let's take a look at our normal distribution to determine what our p-value for this problem is going to be. Remember, we're looking for 2.54. So here's 2.5, here's 0.04, and right there where they meet is that probability of 0.9945. So based on our normal distribution, I have 0.9945, and I get the probability that any value falls to the right of our test statistic is 0.0055. This is our p-value, our probability value, which we will compare to our significance level alpha whenever we get a value for alpha. We just found the p-value for a right-tailed test, right? That's exactly what we did, that the p-value is going to be the area to the right of our test statistic. We've done that. What if I had a left-tailed test? If I had a left-tailed test, I'd get a test statistic and I'd want the area to the left of that. What if I had a two-tailed test? What we need to do is if I have a two-tailed test, I will look to where my test statistic falls. It could fall to the left of center, right here, or to the right of center. If it falls to the left of center, what we're going to do is look at twice the area that we have. If it falls to the right of center, I'm going to look at twice the area we have. The reason we do this is because for a right-tailed test, for a two-tailed test, that alpha value is going to be split to the left and to the right. What we want to do is put that whole alpha value either all the way to the right or all the way to the left, depending on whether that test statistic is to the right or left of center. We'll go through examples of this later. We do have a quick word of caution because we have lots of p notations. So the p-value is the probability that the test statistic is at least as extreme as one that is obtained. Lowercase p is our population proportion, and p hat is our sample proportion. An alternative option to the p-value method is what we call the critical value method. And in the critical values, we use this to separate the critical region from the values of the rest of the test statistic that do not lead to the rejection of the null hypothesis. One of the main differences between the p-value method and the critical value method is that we can determine the p-value without an initial alpha value. For the critical value method, we need an initial alpha value. So let's take an initial value of 0.05. Because I have a right-tail test, that tells me the critical region is going to be all the way to the right of the critical value. And this critical value will be the z-score that corresponds to having an area all the way to the right of 0.05. Well, to figure out what that critical value is, we need to look at our normal distribution chart and find a value that has an area to the right of 0.05. But again, our table tells us areas to the left. So to compute that, I can just do 1 minus 0.05 and get 0.9500. That critical value that now has an area to the left of 0.95 will be our critical value. So let's take a look. So I'm looking for an area to the left of a z-value of 0.95. And here I see I have two values that are equally far apart from 0.95. I have 0.9495 and 0.9505. And again, we said if that we had two values that were equidistant from our requested value, we would take the mean of them. However, we get kind of lucky because having an area of 0.95 is a very common one, and our table does it for us. That our z-score that has an area to the right of 0.95 is going to be 1.645, and we can take that to our values. So our critical value will be z is equal to 1.645. However, we can use our same test statistic value of z is equal to 2.54. And what we want to do is we want to look to say, well, where does that value lie? And 2.54 is going to fall somewhere to the right of our z-score of 1.645. It falls inside our critical region. And that is how this critical values method works. So once we have our p-value method or our critical value methods, how do we determine whether we can reject the null hypothesis or whether we fail to reject the null hypothesis? And here, if our p-value is less than or equal to alpha, we can reject our null hypothesis. The little mnemonic device is if p is low, the null must go. If our p-value is greater than alpha, then we fail to reject the null hypothesis. The way we would state our conclusion here is there is sufficient evidence to support the claim that the majority of consumers are uncomfortable with drone deliveries, that we were able to reject the null hypothesis. For the critical value method, what we look for is if our test statistic is in the critical region, then we reject the null hypothesis. However, if our test statistic falls outside of it, it's outside the critical region, we'll just call that CR, then we fail to reject HO. And so we saw from our example that our test statistic was in the critical region, the area to the right of the z-score of 1.645. So even that method too also says that we can reject the null hypothesis. I know we only went through one example. The purpose of this section was to gain an introduction into of what hypothesis testing is. We've done all of the steps. In subsequent videos in this section, we will go through more examples of how to do hypothesis testing. We will find other null and alternative hypothesi. We will determine whether we're using a p-value or a critical value method. We'll find test statistics and use this formal method to either reject or fail to reject future null hypotheses. I hope this was helpful. If you have any questions, feel free to email me, and I'll talk to you next time.